Next, let's look at another two-pointer algorithm. This time, usually it's used for linked lists. It's called the fast and slow pointer algorithm. It can also be called Floyd's tortoise and hare algorithm. The tortoise is essentially the slow pointer and the hare is the fast pointer. It can be used for a lot of things. The first example we're going to look at is pretty trivial. It's finding the middle of a linked list, which can actually be accomplished without this algorithm. The easiest way to determine the middle of a linked list would be to, count the length. So 1, 2, 3, 4, 5. So we have the length and then we would find the midway point. When we have a linked list that's odd length, it's pretty straightforward what the midway point is here. But what if we actually had a linked list of even length? What would we define the middle? Well, we have two middle nodes. We could say this is the middle or that's the middle. Let's say that for this question, we assume this is the middle node. So of the two middle nodes with a linked list that's even length, we would take the second one and say it's the middle. So by calculating the length, we can also solve this problem in O of n time. We just have to iterate through the linked list, find the length, then start at the beginning again, and then iterate through half the list, and then we would find the midway point. That's a linear time algorithm. Now this two-pointer technique, fast and slow pointer, is also going to be a linear time algorithm. So there's no improvements with this algorithm, but I think it's important to understand because it can be applied in many different areas, which we're going to talk about here. The idea is that we have two pointers, a fast pointer and a slow pointer. We initialize them at the head of the linked list. Now on each iteration of the loop, we're going to take this fast pointer and shift it by 2 spaces. That's why it's the fast pointer. The slow pointer is going to be shifted by 1 space each time. That's why it's the slow pointer. The fast pointer is clearly twice as fast as the slow pointer. We're going to keep doing this until one of the pointers reaches the end of the linked list. Now it's no surprise that the fast pointer is going to reach the end before the slow pointer. So again here, the fast pointer is going to be incremented by 2 positions and the slow pointer is going to be incremented by 1. When we say reach the end of the linked list, that means the fast pointer is either at the last node in the linked list or it's equal to null. So in this case, we would say the fast pointer is at the end of the linked list. Now, you tell me, if the fast pointer traveled the entire length of the linked list, how far did the slow pointer travel, given that it's traveling half as fast as the fast pointer? Well, the slow pointer would have traveled half the length of the linked list. That means by the time the fast pointer reaches the end of the linked list, the slow pointer should be at the middle of the linked list. And you can see it works out perfectly, at least when we have a linked list that's of odd length. How would it work out if we had a linked list that's of even length? Let's assume this node doesn't even exist. In that case, fast pointer again would be shifted twice. It's not quite at the end. Slow pointer would be shifted by 1. Now that's after 1 iteration of the loop. Let's give it 1 more iteration. The fast pointer would be shifted twice. Here it would be null. This 4 we're assuming is pointing at null. This node doesn't even exist. Slow pointer would be incremented by 1. So this is after 2 iterations of the loop. The fast pointer reached the end of the linked list. The slow pointer is once again exactly where it needs to be. It's at the midway point because we defined the second node as being the midway point when we have a tie like this one, when we have linked lists of even length. So it worked out perfectly in this case. But what if we had defined this as being the middle? When we have a tie, we actually want the first node to be considered the middle. Well, it wouldn't be very complicated actually. We would just have to augment this algorithm slightly. We would initialize the slow pointer here, and we would initialize the fast pointer here. And then we would increment this twice, and then we would increment the slow pointer once. Fast pointer has reached the end, slow pointer has reached the middle because now we're saying that this is the middle of the linked list. The idea is that the fast and slow pointers can be used to find the middle of a linked list. So this is what the code for that would look like. It's more simple than you would expect. We just take 2 pointers, slow and fast, initialize them to the head of the linked list, while the fast pointer is not null, and while the fast pointer dot next is not null. This basically means while we have not reached the last node of the linked list, because if we did, then fast dot next would be null, so then we would also stop. But while that's not the case, we're going to increment the slow pointer by 1, set it to slow.next, increment the fast pointer twice, set it to fast.next.next, and then continue doing that until the fast pointer reaches the end of the linked list, and then we would return slow, which should be at the middle of the linked list. And by the way, what if we were given an empty linked list, a null linked list? This algorithm actually would work as well. That's the beauty of it, because slow and fast would be initialized to head. Assuming head is equal to null, this loop would never even execute, and we would end up returning slow, which is equal to null. So it does handle all the edge cases that we're looking for. But there's one thing we haven't talked about. What if the linked list actually had a cycle in it? That means, what if this node, 5, actually was pointing at a previous node like 3? That would mean as we traverse this linked list, we would never stop. This loop would never stop. We would get to the 5 and then go back to the 3 and then back to the 4 and back to the 5. This algorithm would run forever. But believe it or not, fast and slow pointers can actually be used for cycle detection. Let's take a look at how that is. Suppose we're given a linked list like this one, which clearly contains a cycle. We start at the 1, we go to the 2, we go to the 3, the 4, the 5, and then we end up back at the 2. So we see that there's some portion that's not a part of the cycle, but eventually there is a cycle. And that's the part that we're going to get stuck in. This might not necessarily exist. This might have been longer. We might have had 2 or 3 or 4 nodes before the cycle, or we might have had none at all. But the point is that there's a cycle. Now, given any arbitrary linked list, we want to determine if it has a cycle or not. Now, if a cycle does exist, that means as we traverse the linked list, we will eventually see the same node twice. So eventually, in this case, we will see the 2 twice. Now, we would also see the other nodes twice if we kept traversing, but this would be the first node that we saw twice. How can we detect that? How can we detect duplicates? Well, the easiest way would be using some kind of hashing data structure, in this case, a hash set. If we're told that the values of each node are unique, we can use that and add them to the hash set, but we might not be guaranteed that. So an easier thing to do would be take the pointer of every single node and add it to a hash set. Then if we ever visit the same node twice, in this case, we would eventually get to the 2 node, we would see that it's already been added to the hash set. That means this is a duplicate node. That means we somehow visited it twice. So of course there must be a cycle in the linked list, and then we would return true. But what if there's not a cycle? What would happen? Suppose this 5 didn't point at anything. Suppose it's pointing at null. Well, in that case, we would have a pointer, and then it would keep iterating through the entire linked list until eventually it reached null. If we reach null, that's the end of the linked list. So of course it can't have a cycle, so then we would return false. The only problem with this is it's taking us extra memory. We have to take every single node and add it to a hash set. That's taking O of n time complexity, but also O of n memory complexity. How can we eliminate this extra memory need? Well, you guessed it, the fast and slow pointer technique. First, I'm going to walk you through this algorithm, and then we're going to discuss why exactly it works. So once again, we start with 2 pointers. We initialize both of them at the head. One is going to be the fast pointer and one is going to be the slow pointer. We're going to increment the fast pointer by 2 spaces. So 1, 2, so it's going to end up over here. We're going to increment the slow pointer by 1 position. So it's going to end up over here. So this is what the pointers would look like after 1 iteration of the loop. Next, again, we're going to increment the fast pointer by 2 spaces. So it's going to end up over here. The slow pointer is only going to be incremented by 1 position, so it's going to be over here. Fast pointer, once again, is going to be shifted by 2 spaces, so you might naively think, well, looks like the fast and slow pointer are intersecting. But we're simultaneously shifting the fast and slow pointer at the same time. So the fast pointer was shifted twice. That means the slow pointer has to be shifted once. So actually, they were not overlapping just yet. But now we're going to shift fast pointer 2 spaces 1 more time. So fast pointer will end up over here. Slow pointer will also end up over here. It's going to be shifted by 1. So now they are intersecting. If the fast and slow pointer intersect, then we know there's a cycle in the linked list, so we can return true. But now let's talk about why is it that if the 2 pointers intersect, that implies that the linked list has a cycle? Well, the idea is actually pretty simple. We have 2 pointers. The fast pointer should always be ahead of the slow pointer, and that is the case. Here the slow pointer was here, the fast pointer was here. Next, the slow pointer was over here, but the fast pointer was already a few spaces ahead. But if it turns out that we have a loop in our linked list, a circle of some kind, that's the only way that the slow pointer would be able to catch up with the fast pointer. Because if our linked list was a straight line, the fast pointer would always be twice as far ahead as the slow pointer. But that's not the case. Here we had a circle, a loop, so the slow pointer was able to catch up. So that's how we know we have a cycle, but why is it guaranteed that the slow and fast pointer are going to intersect? What if they never intersect? Then we would never know if we have a cycle or not. Well, if we do have a cycle, it's guaranteed that they're going to intersect. Why is that? Because the fast pointer is going twice as fast. We saw that at the beginning, they start at the same position, but eventually the slow pointer and the fast pointer have both entered this cycle. In this case, it's a cycle of length 4. If they're not at the same position, in this case, they're not at the same position, there must be some distance separating them. Previously, I said the slow pointer will catch up to the fast pointer, but that's not quite true. Actually, the fast pointer will catch up to the slow pointer. It's going to overlap it. So here, you can see that the distance between the slow pointer and the fast pointer is 1, but the fast pointer will be the one that catches up. So the distance between the fast pointer and the slow pointer is 1, 2, 3 spaces. But if the slow pointer is moving by 1 and the fast pointer is moving by 1, 2 spaces, then the distance between them should be shrinking by 1 every single time. When we took our slow pointer and shifted it over here, and we took the fast pointer and then shifted it by 2 spaces, the fast pointer was over here. Now what's the distance between them? Well, the fast pointer only has to move 1, 2 spaces now, 2 spaces to catch up to the slow pointer. So the distance went from 3 to being 2. It decreased by 1. And again, the slow pointer is shifted by 1 over here. The fast pointer is shifted by 2 to be over here. Now the distance between them is only 1. It keeps shrinking by 1 every iteration of the loop until finally one more iteration, the fast pointer was shifted by 2 to be over here. Slow pointer was shifted by 1 to be over here. Now the distance between them is 0. They've intersected, so we know we have a cycle. So at this point, we can return true. That's why we're guaranteed that the 2 pointers are going to intersect at some point. And the last claim that I want to make is that this intersection will actually happen in linear time. We're guaranteed that it's going to happen in linear time. The reason is that eventually the slow pointer will have entered the cycle over here. The fast pointer is also a part of the cycle. The distance from the fast pointer to the slow pointer can't possibly be longer than the length of the cycle. In this case, it's 3, where the length of the cycle is 4. So if the length from the fast pointer to the slow pointer is 3, how many more iterations of the loop is it going to take us for these 2 pointers to intersect? Well, of course, it's going to be 3. So basically what I'm saying is, by the time the slow pointer enters the cycle, the slow pointer won't have to traverse longer than the length of the cycle. And we saw that the slow pointer went here, then here, then here. It never had to loop multiple times. So what I'm saying is the slow pointer will only have to iterate through the entire length of the linked list. The fast pointer, of course, will have to iterate through 2 times that. So we could say that the overall time complexity is maybe 2 times n, where n is the length of the entire linked list, but we know that will also reduce to big O of n. So that's why this is always going to be a linear time algorithm, because a slow pointer won't possibly have to iterate through longer than the entire length of the list. So the fast pointer will have to do twice that much, but that's still a linear time algorithm. So the code, once again, is actually going to be very simple. We have 2 pointers, initialize both of them at the head while the fast pointer has not gone out of bounds. If the fast pointer reaches null or reaches the last node of the linked list, that means there can't be a cycle. So this loop would stop and then we would return false. But if that's not the case, we will keep shifting the pointers, slow pointer by 1, fast pointer by 2, and if eventually they are equal to each other, we will return true. That means we do have a cycle. So if this whole idea of cycle detection was not confusing enough, now let's look at one last example. So suppose we're given a linked list and we want to determine if it has a cycle, but in this case, if it does have a cycle, we want to return the head of that cycle. If it doesn't have a cycle, then I guess we can just return some default value like null. What is the head of the cycle? Well, in this example, we have some portion that's not a part of the cycle, but the beginning of the cycle starts here. So that's what we would return. Now, we might not have had this node at all. Maybe this is the head of the linked list, so this would also be the head of the cycle. The beginning of the linked list is a part of a cycle, so that's what we would return. Or we might have a bunch more nodes that come before the cycle. So this problem can also be solved with a fast and slow pointer. So what I'm going to first do is show you how to solve this problem. The solution is surprisingly simple, but next we're going to understand why it works, which is not as simple. So we're going to have 2 pointers, a fast pointer and a slow pointer. We're going to shift the fast pointer by 2 spaces, same as we did earlier. So fast pointer would be over here. Slow pointer is going to be shifted by 1. It's going to be over here. Then again, fast pointer is going to be shifted twice until it's over here. Slow pointer is going to be shifted by 1 until it's over here. Fast pointer is again shifted twice. It's over here now. Slow pointer is shifted by 1. It's over here. Now lastly, fast pointer is shifted twice until it's over here. Slow pointer is shifted by 1 until it's over here. So basically we do the same thing that we did earlier until the 2 pointers intersect. Of course, they might not intersect. Maybe the fast pointer goes out of bounds. In that case, we would return null as the result. But in this case, they do intersect. That's when we know we definitely have a cycle. But the 2 pointers don't necessarily intersect at the beginning of the cycle. So we know for sure that they intersect here, but now we don't know how many more spots do we have to move before we get to the head of the cycle. Well, the solution is actually really easy, but very unintuitive. We have a slow pointer here. What I'm going to do now is create a second slow pointer, and I'm going to set it back to the beginning of the linked list. So I'm going to call that S2. It's the second slow pointer. S1 is still over here. Now, at this point, we're going to forget about the fast pointer. We don't even care about the fast pointer anymore. All we know is that the slow and fast pointer intersected over here. At this point, we're going to increment the second slow pointer by 1 every time. That's why it's called the slow pointer. And we're also going to increment the original slow pointer. And it's still over here, by the way. We're going to increment it by 1. We're going to shift it by 1 every time. These 2 pointers are guaranteed to intersect at the start of the linked list. They're guaranteed to intersect here. And when they do intersect here, that's the node that we would return. So when we're asked to return the head of the cycle, this is what we would return. So it works perfectly. And it's just that simple. If you just want to know what the algorithm is, what I described to you is the entire thing. And luckily the code for it is not super complicated either. It just has a second loop. So what we would do is the first portion of the algorithm is where we start at the head and we keep shifting our slow and fast pointers until they equal each other, in which case we would break out of the loop. Or here where the fast pointer might go out of bounds, that would mean we reach the end of the linked list. So here after that while loop stops, we have a condition to check, did we reach the end of the list? Because if that's the case, then we can just go ahead and return null. But if we didn't reach the end of the list, then we have the second phase that I just talked about, where our slow pointer, our original slow pointer, is still where it initially was, is still where it left off, but now we create a second slow pointer at the head of the linked list, and here we keep shifting these 2 pointers by 1 each time until they equal each other. We know they will eventually intersect and that they will intersect at the head of the cycle. And when that happens, we return that head. So that's the algorithm itself. Now let's talk about why it works. So let's say we're given some arbitrary linked list where it has some portion before the cycle and it has a cycle of arbitrary length. Of course, here the cycle is of length 4, but let's assume this is some arbitrary linked list where the cycle could be of any length. We know that at some point in the linked list, the two nodes are going to intersect. Let's just call this arbitrarily the point of intersection. So I'll mark it with an X. We have 3 portions here. We have this part, which I'm going to call P. It's the portion before we actually get to the head of the cycle. It could be 0 if this portion didn't exist, right? But here we're assigning some variable to it. The length of the cycle itself, I'm going to call C. Now, the length from the beginning of the cycle to the point of intersection, I'm going to call the length of that equal to the length of the cycle minus X. Now this X is not to be confused with this X over here. I just, put some symbol over here just to say that this is the point of intersection. Maybe I'll just make it a circle instead. Then the last thing would be that the remaining portion of the cycle is going to be X, because we know that the entire length of the cycle is C. So if this portion is X, then the other remaining portion should be C minus X. I know this is a little bit confusing, but I'm just setting up the math here. So recall that the slow pointer travels twice as slow as the fast pointer. That means if the fast pointer covered this much distance, then the amount of distance that the slow pointer covered multiplied by 2 is going to be equal to how much the fast pointer covered. Like, this is just distance here. 2 times the slow distance is equal to the fast distance. And we know that's always the case, and we know that both of the pointers are going to intersect at some arbitrary position. So what distance will the slow pointer have to travel anyway? Well, it would start at the beginning. It would have to travel this P distance, and then it would also have to travel this C minus X distance. And remember, this could be arbitrary. It could be at, it's here, it could be here, it could be here, it could have to travel the entire loop. But the slow pointer, we know, won't have to complete multiple cycles. It won't have to go through multiple laps of the cycle for reasons we talked about earlier. So this is the distance the slow pointer will have to travel. The fast pointer will also have to travel this P distance. It'll also have to make an entire loop through the cycle, which is, we know, C, and then it'll also have to travel this portion, C minus X, and then the fast pointer will arrive at this spot. So by the time the pointers intersect, so this is the distance that they would have to travel. We know that the slow pointer has to travel P plus C minus X, which is the length of this portion. And we know that 2 times the length that the slow pointer traveled is equal to the length that the fast pointer traveled. And the fast pointer has to also travel this P portion. Then it has to make an entire cycle around here, which is where the C comes from. And then it has to travel this last portion, which is C minus X, which is where this comes from. Now we can do a little bit of algebra. We see both sides will have 2 C's, so we can get rid of those 2 C's. We know both sides have one side has a P and the other side would have 2 P's, so we can get rid of the P on this side. This side had minus 2x, this side had minus 1x, so we add an x to both sides. Then we're left with P minus X is equal to 0, so we can solve for P. P is equal to X. So we went through all that math just to find that P is equal to X. But it makes sense because what we found is this length, after the 2 pointers intersect, the length from that node to the head of the cycle is equal to the length of the beginning to the head of the cycle. We don't necessarily know what that length actually is. If we did, it would be easy. But because we don't know what that length is, we don't know what P or X is, what we say is we'll keep a slow pointer over here and we'll keep a slow pointer over here. We don't know how far we're going to have to travel, but we know that if we keep shifting the 2 pointers by 1 each time, eventually when they intersect, they will intersect at the head of the cycle. And then that's what we can return. So that was quite a lot and probably more math than you were expecting. It's okay if you don't completely understand this, and it's especially okay if you wouldn't be able to come up with the math proof yourself on the spot. But fast and slow pointers are a common technique to solve difficult problems like this, and what we talked about can be an interview question that comes up, so I think it's worth understanding. Even if you're just going to memorize the algorithm itself, because it's not a complicated algorithm, the proof is what's complicated in this case.